All right, hello everybody. This will be a second attempt at recording this video today. First one didn't get any audio, which is a bummer. But anyway, I wanted to solve a problem that the task of this problem is to compare two binary trees. And I think it's a very good problem to actually solve and learn how to solve, because the underlying algorithm is learning how to implement Depthfirst search. So what our task is, given two binary trees, we need to write a function that will check if they are the same tree type or not. And we are actually not only looking for the values, but we are also looking for structural identity. What that means is, for example, if you see in this case, we see that not only the values are the same, but also the nodes, right? In this case, we see that the values are the same, but for this node, its left child is the 2, and for this node, its right child is the 2. So basically, our output would also look differently, and this would give us this would kind of tell us that those trees are not the same. So what I initially did was think about it as we would have two queues. One would be a queue that will, for example, we will call it a queue, and for our first element would be basically we would put the first element we see. This will be our input, and we would also have a result, basically buffer. And since our queue only has this element, we will start our loop and we'll get this element from here, put it here, and for each of those elements that we put here, we also see its children, right? We look at its left child, there is a 2. We look at its right child, there is a 3. And after we are done with this element, we basically pop the next element out of the queue. We put it in our result because we have visited that node, and now we look at its children, and left child is a none, right child for the 2 is also a none, and we are done with the 2. And this is basically how a depth-first search would work. It will always go from one basically to always go to the throughout the depth of a single path in the tree, then go back, then go to the second. Yeah, was it like that? Well, it would definitely not go sideways. It will always try to work its way downwards the tree and slowly go sideways. By comparison, Breadthfirst search would basically work around the tree sideways. And not downways or downwards. So when we are done with this element, we have to pop the other one or the next one from the queue. We put it in our result, and now we are looking at this one that we just popped. Left child is a none, right child also a none, right? Okay. And we continue with the queue. We take the element from the queue, put it there, and when we see that our element is a none, we know that there are no children there. We wouldn't really be able to put anything in the queue. That's why we just leave it in the queue and go over to the next one. And as you can see, of course, for all those other ones, would be getting the same result because they're all none. And essentially our queue is now empty, so this algorithm will have to stop. This is the end result, and we do this for both trees, and at the end we only have to compare the two results. So let's just do exactly this. I will call, since we have two trees, I will just go pragmatically with this. It's kind of easier to see what's happening like this. I'll just call a Q1, a result1 for the first tree, and a Q2 and result 2 for the second tree. In our first queue, we would definitely already put Q1 append. We would put the first element that we got from our input, or basically the first node, right? For the second tree, we do the same. So we put this second node from our input here. So let's do our algorithm for the first tree, and since it will be the same for the second one, we can basically copy that result. So while our Q1, well, basically while the length of Q1 is greater than 0, we know there are elements in the queue. We would basically have, how did I call it, current node would be our queue pop. Basically the furthermost left element, or the oldest element in the queue, will be taken. In this case it will be the 1, right? So now what I did before, and I'll just write it like that, but in the end the structure will change a bit and you will see why. Let's think about this as if we're currently thinking about this problem. So we basically have our current node, right? What we want is to add this its value to the results. And result 1 would have this current node and its value, and you can see here the structure of the 3 nodes and how to access them. So and we also, after we have put our current value from the queue into the result, we also want to look at its children, right, and put them into the queue. So we would basically append from this current nodes left and right children. Okay, and our approach should basically work if there were no none values. Why would it work if there were no none values? Well, you would basically do the same thing that we spoke in the beginning. We're taking elements from the queue, putting them in the result, and we are also returning some of its children to be processed in the queue further, well, later on. The only issue is that once we take a current node, we cannot really append values if it's not a tree node. So that was my mistake last time, and I actually fixed it really easily, but it just kind of messes up with the thinking logic here, because the first moment when you take an element, you'd actually already have to see if the element is a non-value, and if it is already a non-value, we are also appending it to the result, of course, as a non-value, just to simplify everything. And we also want to skip all that parts, because we know if it's a non-value, we wouldn't really have anything here to add for, and we wouldn't even be able to see any left or right children, right? Because yeah, it's an empty node. So if we get an empty node, we add it into our results, and we basically skip that part and we go over again to the queue, see what's left in the queue. And this should be our implementation when it comes to the Breadthfirst search for a tree. We can literally copy the same thing and just replace everything that has basically now work with the second tree. And in the end, we should have the results 1 and 2 containing exactly what is contained in those 2 trees, including the non-objects. So the non-objects would give us an idea of the underlying structure. We can even just print them just to see how this looks like. I'll just return true for the function to execute, but we don't really care at the moment. We just want to see how our results look like. And in this case, it is very important to kind of learn just a sec. Yeah, it's a Q1. Sorry, maybe I have some other ones here as well. Q2. Everything else should be indexed properly, I think. So, as you can see, first of all, very important algorithm. Just try and work with it yourself. Try and actually implement it yourself. Figure out and try to figure out the idea behind it. And I can tell you that the first time I had to implement this was, or the last time I had to implement this was in my data structures and algorithms course, which is in my second semester, so like, I don't know, like 3.5 years ago. And I know it took me quite some time, but today when I had to do it again, it took me like 5 minutes. So it definitely helps for you to kind of go head on with the problem, understand it, and later on you can implement it in other languages and all that. I remember doing it in Java first time, so it's like you basically kind of already know what's happening. You just have to figure out some language specific details, implementation specific details, and everything else is kind of like trivial. So yeah, practice it on your own. This is very important. Such questions, such approaches come very often in these type of technical interviews, from what I know. And yeah, it's just very useful to know. So let's go back to our prints. As we can see, at least for this example, and this is basically yeah, it's something that I wrote last time as an example just to see how it will turn out. It's basically two of this same tree, right? What we get is we go over for the first node, we see it's a 1, we put it in our result. We look at its left child, it's a none. We put it into into the queue, and we take we look at its second child or the right child, it's a 2. We put it also in the queue, and then we take from the queue the non-value. We see it's a non-value, we just put it in the result. Then we take the remaining 2 from the queue. We put it here, and we look at its children. Left one none, right one none. They both end up in the cube and eventually end up here because we wouldn't do anything with them. So as it looks like, our structure output is doing what it's supposed to do. I can actually do something like this, just as in this example. And we will basically get 2 different structures. As you can see, you can kind of practice on your own why this looks like this. And yeah, one last thing, since at the end we are also trying to compare, right? We have result 1, we want to compare it to result 2, and we are expecting to see a true if both of them have the same structure. And we are kind of assuming that, okay, if we see that the numbers are the same, the order is the same, that things are going to be acting the same. But just keep in mind that some things are not the way they look like or they seem to be when it comes to programming languages. For example, for Python, the non-values will equate to true if you compare 2 of them. But if you go in work for something like data science, data engineering positions, or just general company that has to work with a lot of data, you'd be working with something like Python, for example, or pandas. And in Python, it turns out that if you compare 2 non-values, you would actually get false, because each value has something. It's not they are not created equal. I don't know how to explain it, but they wouldn't compare the same way. So do not go programming programming, do not assume things. Test everything that you come up with, and do not try to answer your questions just based on logic. You have to kind of read through documentation, or just try and test every question that comes to mind, so you are sure what you're writing for is actually what you want to be writing for. So yeah, that was just a tangent. I know I had this issue before with some programming tasks, and I think it's important to note for, yeah, just to save you some trouble, I guess. And yeah, our algorithm was a success. This is the solution to it. I hope you learned something. I hope it was useful, and just practice. And yeah, have a good day and see you next time.